Hello everyone, my name is Elsa Teng. I'm a second-year PhD student in UC San Diego, and I'm working with Professor Karin Sandstrom on ALMA observations toward nearby galaxy centers. Today, I will present one of our results on the galaxy NGC 3351. So our motivation is to study the CO to H2 conversion factor, alpha CO. And this is defined as the H2 mass over the CO1 to 0 luminosity. So this factor is important because we know that molecular hydrogens are not directly observable in cold environment below 100 Kelvin. So the most common way to trace the star-forming gas with a low temperature is to observe the CO emission and then apply a constant alpha CO to derive the total H2 mass. However, recent studies have shown that alpha CO varies with environmental conditions like temperatures and densities. And recent observation also shows the alpha CO is lower in the centers of many nearby starburst galaxies. And one of them is our target NGC 3351. So here's an image of NGC 3351 from the Sloan Digital Sky Survey. The red box here shows our observed region in the central 1.5 kiloparsec. So we observe with ALMA in multiple CO, 13CO, and C18O lines with an angular resolution of 1 arcsecond. And here is our observed moment zero maps in all 6 lines. So it is clear that we see a star-forming ring around the nucleus, around the central 1 kiloparsec region. And to determine the physical conditions of different regions in the galaxy, we use radix to model the flux under various combinations of physical parameters, which include the H2 density, kinetic temperature, CO column density per line width, the 2 CO isotopic log abundances, and the beam filling factor. And then for each pixel on the image, we compare these models with our observations, and then compute the chi-square values and probability distributions to get a best fit or the highest likelihood physical parameters. So here we show an example of a bright pixel near the northern part of the ring. So in this plot, we show how the best fit solution here is constrained by the 6 observed line flux. So these constraints are given by the flux uncertainty defined here, including the measurement uncertainty and a 10% flux calibration uncertainty. And another plot below here shows the marginalized 1D and 2D likelihood distributions. So we can, for example, extract the parameters that corresponds to the peak of these 1D likelihoods. And then by iterating this procedure over each pixel on our image, we can then produce a map like this, showing the highest likelihood physical parameters at each pixel. So here we can see some interesting results. For example, in the temperature distribution, we see that the temperatures are higher near the nucleus and the contact points that connects to the spiral arms, which here we will call them spiral arms, but note that they are not real spiral arms caused by density waves, but more like a gas inflow driven by the bars at the galaxy centers. Also, we find that the CO isotopic log abundances are pretty uniformly distributed in the central region of the galaxy. And we find that the derived values are very similar to the Milky Way values at the central 1 kiloparsec. So since now we have the CO column density map derived, we can base on the map and derive the spatial distribution of alpha CO, just by plugging in the CO intensity we observed and by assuming a CO to H2 abundance ratio. So here is the derived alpha CO distribution. And we find that most pixels from the central region has an alpha CO value similar to the Milky Way average, as indicated by the black dot here. But for the spiral arm regions, we see a substantially lower alpha CO value than the galactic average. And here is another plot showing the relation between the derived CO column density and the observed CO intensity. And this black line here shows the Milky Way average. So here we separate the pixels from the spiral arms and the centers, and we can clearly see that even with the arrow bars, there are still many pixels from the spiral arms having lower alpha CO value than the galactic average. And another plot here shows the relation between the derived alpha CO and the galactocentric radius of NGC 3351. Again, we can see there is a clear drop in the alpha CO values at around a radius of 10 arcsecond, which is exactly where the spiral arms and the ring intersects. So to discuss the implication of our results, first, it is clear that we see lower alpha CO values in the spiral arms, and we think this could be supported by our observations. So for example, we find that the CO to 13 CO line ratios are significantly higher in the spiral arm regions. Also, from the figure on the right, we can see the velocity dispersions are also higher in the arms. And this may indicate a more turbulent environment or the existence of shear forces in these bar-driven gas inflows. And these are also consistent with our derived optical depths. So here we can clearly see that the optical depths are lower in the arm regions. We think these can all explain why the conversion factor is low in the arms, because we know that either a higher velocity dispersion or a lower optical depth can allow more CO emission to escape, so that we would observe more fraction of CO emission and therefore observe a lower conversion factor. Finally, we derive a mean alpha CO of around 2.5 in this region, which is higher than the value determined by Sandstrom et al. 2013. But since we are using different methods, we have different assumptions on the parameters, and also the data we use have very different angular resolutions. For future work, we will identify giant molecular clouds in the galaxy to derive the alpha CO based on virial methods. And we will compare the alpha CO derived with our current results from multi-line modeling. And since we also have ALMA data on other two galaxies, we will also conduct similar analysis on those data and compare with our current results. Thank you.